Okay, today I am going to be doing another mechanics paper with you. So this is the October-November 2023 paper 4-1 for mechanics. I am sitting here, I've got my calculator with me, and I've got 19, and my goal is to see how fast I can do this. Maybe not, I would like to explain as well as I go, but I'm going to try and do it as fast as possible, and hopefully as accurately as possible. Okay, let's just jump right in. So, a particle has a mass of 1.6 kgs. It's projected with a speed of 20 meters per second up a slope. Okay, so I'm just going to draw here. It is projected up the slope with 20 meters per second. Okay, and my angle of my slope, tan theta or tan alpha, is 3/4. Okay. Use the energy method to find the distance the particle moves up the slope before coming to instantaneous rest. Okay, so this particle is projected up. When I look at energy, I want to know, am I looking at potential energy, kinetic energy, work done, again, well, by driving force, and work done by friction. So because then I'm going to take a snapshot between the bottom of the hill and going up the hill. So if I compare my bottom to my top, I need to take into consideration that potential energy is changing. Use the energy method to find the distance. Okay, so my kinetic energy is going to change because it has an initial velocity of 20, and then it's coming to instantaneous rest, which means it becomes still. Okay, work done by a frictional force. There's no force pulling, there's no engine or something pulling on this. And it is going up a smooth slope. So we also don't need to look at the work done against friction. Okay, so all I've got is my potential energy is changing. So in the beginning, potential energy is 0. And at the end, or final potential energy, there will be some potential energy there. So I'm just going to actually cross that out. Then I've got kinetic energy in the beginning, and I've also got no kinetic energy in the end because it comes to rest. So basically what's happening here is all my kinetic energy that the particle has is going to be converted into potential energy. Okay, so if I were to write out my formula for kinetic and potential, all the kinetics becoming potential, I don't actually need mass. Mass cancels out in both cases here. The only reason I can cancel it out is because I know my mass is not 0. So here we've got a half 20 squared is 10 times the height. So the height is going to be 20 meters. Now we need to remember that that is a vertical height. Okay, so that's my h going up. So if I look in my triangle, because they want to know, find the distance the particle moves up the slope. Okay, so my sine of alpha is h over my hypotenuse. So I want s, which is 8 divided by sine alpha. My h in this case is 20. And then I've got sine of the inverse of tan 3/4. Okay, my calculator must be in the correct mode. I just quickly need to change it from radians to degrees. So sine of the inverse of tan 3/4. And that gives me 100/3, or 33.3 meters. Let's just see, how do they ask? Use the energy method to find the distance. So they don't say if they want an exact value or not. So you could just say 33.3 meters, that would be correct, or 100/3 would also be correct. Okay, next question. Particle of mass 2.4 kgs. Okay, immediately I want to put in my mass here. It's held in equilibrium. that means the sum of my forces in each direction is 0. Held in equilibrium by two strings, one of which is attached to point A and the other to point B. The string makes an angle of that and that with the horizontal. Find the tension in each of the two strings. Okay, so I'm just going to label it T1 and T2. And then I've got my strategy. My sum of my forces in the x direction should be 0. So I've got minus T1 cos of 35. So T1 has a component in the x direction. And T2 also has a component in the x direction. If I just simplify these, cos of 35 okay, I think I'm going to just make T2 the subject of my formula. Doesn't really matter which one I decide to do, so cos 35 okay, so I've got a value here, well, T2 in terms of T1. Then I can also look at my Y values. They should also be in equilibrium. So I've got T1 sine 35 plus T2 sine 40. So those two have a component going up. And then I've got my weight component going down. Okay. So if I just simplify these, I'm going to change this into my T1, 1.06932 T1, and then sine 40. Sometimes I like to keep just keep my, instead of making decimals, actually keep my trig functions, because then you know that you're going to have the right significant figures. So in this case, I have got, so I've technically got sine 35 plus 1.06. .2609 T1 is equal to 24. So if I say 24 divided by my answer, I am going to get an answer of 19.0 newtons for my T1, and then my T2. Yeah, I definitely do. I might have preferred to just keep this in terms of trig ratios. Okay, that gives me an answer of 20.4 newtons. Those are the two tensions in my string. I would say the tensions in my two different strings, I would say these questions so far have been straightforward. There's not tricks happening in these questions. So you just got to pick up the keywords here. In this case, it's equilibrium. And our strategy for that is the sum of the forces in the x is equal to 0 and the sum of the forces in the y is equal to 0. Okay. Jumping on to our next question. As soon as I see this question, I'm seeing a velocity time graph with straight lines. So I know that I'm working with kinematics, and I know that my area under the graph gives me my distance. And I know that my acceleration is the gradient of the graph. So that's the two key points that I know for this topic. So let's see how we can apply that to this question. So the diagram shows a velocity time graph of a bus. The bus starts from rest and accelerates uniformly for 8 seconds until it reaches that speed. Okay. The bus maintains the speed for 40 seconds. It then decelerates in 2 stages between 48 and 62. The bus decelerates, so that is literally, I've actually labeled that correctly. That's A. And then the other one is 2A. Okay, so here they are saying there's an acceleration and then it's double the acceleration. Okay, until coming to rest. Great. Find the distance covered by the bus in the first 8 seconds. Okay, so we know distance is area under the graph. They want us to know in the first 8 seconds. So I'm literally going to look at the area of that triangle. So my distance is a half times 8 times 12.6. So this is basically the area of a triangle, half times base times height. But I'm labeling it as an S because it is my distance. Okay, and here we get an answer of 50.4 meters. Okay, find the value of A. All right, so now, I know how much I know the distance that it's accelerated for, and I know that it's coming to rest again. So basically, it's got to decelerate. It's got to decelerate and come to rest, and decelerate and come to rest over here. So this thing is going at a constant velocity. So I'm just going to take a look at it's going to okay, let's have a think about this. What are we going to do? So the bus goes forward and then it travels at a constant velocity. So it's traveling at 12.6. So I'm just going to write up formulas here. I'm not 100% sure where this is going, but let me just show you. I'm only going to work with the principles as to what I've got. So that's A and that's 2A. So I know my acceleration is my change in velocity over change in time. In this case, so gonna have to call that V probably. So I'm going from a velocity of 12.6 to V over a time of 48 minus 62. Okay, so it's going to be negative acceleration. And I know that is equal to A. Okay, so I can actually work out what my V, no, I've got 2 unknowns. Okay, so that's fine. Let's just simplify this. 12.6 minus V is equal to 48, well, divided by minus 14 is equal to A. If I was to simplify this, I think I'm going to be doing simultaneous equations. That's what I'm starting to see. This is minus 14A. All right. So, or I could leave it if I'm going to do a simultaneous equation, I might want to make A the subject of the formula. But anyway, let's maybe make V the subject. So 12.6 plus 14A is equal to V. Right, so I've just written up, I know that my gradient is my acceleration. So I've just written up something there. Now I'm going to do another formula here. So I'm going to say my acceleration is my change in velocity over change in time. So this time I'm going from V to 0, and I'm going from 62 to 70, and that is equal to 2 times my acceleration. Okay, so let's move this down here. Okay, so what I really want you to see with this question is sometimes it's not so easy to spot what's happening or what you need to do, but you have to start somewhere. Now that I've started, I can see that this is going to work out quite nicely with a simultaneous equation. Minus 8 is equal to 2A, so V is equal to minus 16A. Right, so because these are the same V, so there's my V there and there's my V there, I can now equate them to each other. So 12.6 plus 14A is equal to minus 16A. That means 30A is equal to minus 12.6. And this gives me an acceleration of negative 0.42, so it's decelerating. But they have said it decelerates at A. So they've already told me it's decelerating. So I don't need to actually give them the minus sign. I could just give them the value of A because they've already said it's deceleration. Okay, so my answer there is going to be 0.42. Okay, so I really hope that that helps. You don't always know what to do, but the two things you do know about these types of graphs is you know the area under the graph gives you the distance, and you know that the gradient of the graph gives you acceleration. Okay, and here we had to do simultaneous equations, which I only figured out halfway through the question. Okay, so just start writing down the things you know. Okay, find the average speed of the bus for the whole journey. Okay, so average speed is a keyword. Speed is change in distance over change in time. So this is a very popular formula. Lots of my mechanics students like using it, except you shouldn't use it. The only times you can use it is if you've got constant velocity, or if you've got average velocity. So because we want to look at average velocity, we're going to use this formula. If they were asking anything else, we would probably rather use SUVite. Okay. So average velocity is change in distance over change in time. So what was the change in distance of this bus? And then the change in time. So if we just look at it, we can see the change in time is 70. The change in distance, I'm going to need to work out the area under this graph. Okay, so we already know the blue triangle. That's 50.4. So my total distance is 50.4 plus my rectangle here is length times breadth. So here my length is 40 and then 12.6. I'm just going to actually put in brackets. 12.6. Now I believe I have a trapezium here. Okay, so if I look at my height of my trapezium, I'm going to say 62 minus 48, and that gives me 14. And then I've got 12.6, and we didn't work out the height of this velocity. That's interesting. Maybe I must quickly go and work that out over here. Minus 16 times 0.42. That gives me a velocity of 6.72. Okay, so for trapezium, you add up your lengths, divide it by 2, and then multiply it by your height, which in this case was 14. And then my last triangle is a half base times height. So that's a half times 8 my base, and then my height was again the 6.72. Okay, so that's my total distance. So let's just work that out first. 40 times 12.6. And a half base times height. So I'm getting a total distance of 716.52 meters. And then we need a total time of 70. So my velocity divided by my time. And that gives me an average of 10.236 meters per second. And because that number ends like it's an exact value, I'm going to give all of those significant figures. Okay, so don't round off to 3 significant figures if it is rounded off already. Okay, if we take a look at the mark scheme, they will give you the marks, but they generally say here non-exact values should be rounded off. So if it's an exact value, you need to give the full value, and if it is not an exact value, then you can round it off to 3 significant figures. Okay, let's jump into our next question, question number 4. Two particles are P and Q, mass of 6 and 2. So let's just start drawing P, Q, 6 kgs, 2 kgs. They lie at rest 12.5 meters apart on a rough horizontal plane. Okay. As soon as I hear the word rough, I must think friction. Okay. The coefficient of friction between the particle and the plane is 0.4. P is projected towards Q with a speed of 20 meters per second. Show that the speed of P immediately before the collision is 10 root 3. Okay, so obviously it's going to slow down because it's got friction. So what I want to do is just start off with drawing a free body diagram. All that we have acting on the particle is friction. So it's projected with a speed, but there's no like pulling force. Okay. If I want to work out my acceleration, I need to use Newton's second law. So the only forces on this thing is friction. And then I've got my mass times my acceleration. So this is my mu r. And my mass is 6 kgs. And I've got some acceleration. Okay, if you in an exam you run out of space, just draw yourself a nice neat column. So I've got minus 0.4. My r is going to be 60. So if I just draw in my r, that's going to be directly opposite my weight. Okay. And so my acceleration in this case, it's actually deceleration, is going to be -4 meters per second squared. Okay, so it's slowing down at -4 meters per second squared. And then I can do suvat now because I know my distance is 12.5. I know my starting speed is 20. I want to know my final speed. And my acceleration is -4. Okay. Okay, so here I've got 20 squared plus 2 times -4 times 4.5. That gives me 300. And then my velocity, let's just write it down, 300. So when I root it, it's 10 root 3. Okay, and we're going to leave it like that because that's what they wanted us to prove. Okay, now there's a collision. In the collision, P and Q coalesce to form R. Okay, so P and Q are colliding. When we look at momentum, so these are two separate particles, find the loss in kinetic energy. Okay, so loss in kinetic energy. So we need to know what's the speeds before and what's the speed after, because speed affects kinetic energy. Okay, so because there's a collision, we're going to go into our momentum equation. Okay, here we've got our mass, so 6 and 2. Oh, and here 6 plus 2, they combined, okay? And it hit particle Q at a speed of 10 root 3. Okay, and Q was actually at rest. So that's technically 0. So now I've got 60 root 3 is equal to 8V. So my V is 15 root 3 over 2. Okay, so I'm just going to leave it like that. They've sort of started the question like that, but we haven't actually answered the question. That's my final velocity. So when we're looking at kinetic energy before and after, we literally, in the collision, P and Q, find the loss of kinetic energy due to the collision. Okay, so I'm going to look just before the collision, and then I'm going to look again just after the collision. Okay, so just before the collision, we only had kinetic energy for our particle P. Okay, and we can just look just before the collision. How much So this is 0.5 times 6 times 10 root 3. Oh, 10 root 3 should be squared. Okay, and that's 900 joules. And then the kinetic energy after is a half, and then we add up both of our masses, and we have to take our velocity and square it. So 0.5 times 8 times 15. 3 squared is 675 joules. Okay, so before was 900, after 675. Minus 675. And that gives us an answer of 225 joules. Okay, so we always just look at a snapshot right before the collision and right after the collision. So there was a loss of 225 joules. Okay. C, the coefficient of friction between R and the plane is 0.4. Okay. Nothing's changing there between each particle on the plane is 0.4. Okay. The coefficient of friction between R, so that's a combined particle. So they're basically just saying it's the same coefficient. Find the distance traveled by R before coming to rest. Okay, so now this is a particle that's now coalesced. It's heading off at a speed of 15 root 3 over 2. But it's got some friction acting on it. So we're going to do the same as what we did in part A. We're going to say minus mu r. Oh, friction is mu r. So minus friction is mass times acceleration. In this case, we've got the full 80 newtons, and then our mass is 8 kgs. So our acceleration is going to be also minus 4. That's just really interesting to note that it doesn't really change between the particles. Okay. Oh, I don't need that now. I need suvat. So I'm going, they want to say find the distance traveled. So I need distance. I know my starting speed is 15 root 3 over 2. The final speed is going to be 0, and my acceleration is minus 4. Okay, and then if I look at my S, take it to the other side. So I've got 15 root 3 my distance is going to be 21.1 meters. That's to the significant figures. You probably could also leave it as a fraction, 675 over 32. Okay. And let's jump to the next question. So here we've got two particles, A and B, and they're connected. So immediately what I'm thinking is this is a connected particle question. We either need to split up the particles and work with forces, or we're going to be looking at energy. So let's just read the question. I also want to know which planes are smooth and which ones are rough. Okay, so the diagram shows a particle A of mass 1.2 kgs. Okay, it lies on a plane of 40, and then we've got 1.6, and that's lying at 50 degrees. The particles are connected by a light string, positive or pulley. The part AP and BP of the string are taut and parallel. The two planes are rough. Okay, great. Well, I mean, that's not what I was hoping for, but that's fine. They've got the same coefficient, and they haven't given it to us, mu, between the particles. Find the value of mu for which the system is in equilibrium. Okay, that's not too bad. 2 pages to answer this, and there's no part B of the question. Okay, so we're going to be doing connected particles. Because we're looking at mu, I'm not going to go into energy. I'm just going to work directly with particles. Okay, I mean forces on the particles. Okay, so if we look at particle B, we know the tension is keeping it up. Because it's on an incline, we have to add the mass. So mg sine of 50. And because there is friction, so this is the question now. Which direction of motion is this going to want to move? Okay, so let's just quickly talk about that. Here we can see that B is heavier than A. Okay, so it's probably going to go towards B. B is also on a steeper slope. So without a doubt, it's going to go towards B. If B was heavier, but the slope was less steep, it could go either way. Okay, so in this case, they have been kind to us. It's not a question about which direction it's going. If B wants to slip down, that means friction of B is going to act up. Okay, so let's write up our Newton's law for this. So we've got only these 3 things. We've got, and our direction is going to go down. That's positive. So I've got mg sine theta, which is 16 sine 50, minus my tension, minus my mu, times my r. Okay, if I just quickly dive into this, r should be straightforward because there's no other components in the y direction. This is going to be mg cos. Okay, minus mu times my mg is 16 cos 50. And they say this thing is in equilibrium. Okay, so it's going to be equal to 0. All right, so we've got tension and we've got mu that are 2 unknowns. I kind of wonder if this is going to be easier to work with it as a system. So I might just write up a third equation. I'm going to write this one for now. I'm not going to simplify it because I actually think it's going to be easier if I use my third equation. Let's just figure out what's happening for each of these though. Okay, this is going to want to move up. That means friction acts down. Tension is pulling it up, and mg sine theta is pulling it down. Okay, so I've got tension pulling it up minus my mg sine theta. So in this case, it's 12 sine 40. Minus 12 sine 40 minus mu times 12 cos 40 is also equal to 0. Okay. I can combine these and look at the system. So what happens when I look at the system? I actually don't need to look at t values because they kind of cancel each other out. Here I've got my mg sine 50. Let's just write this mass in. So this is 16 sine 50, and I've got friction, which is mu times 16 cos of 50. And for my A, I've got 12 sine 40. And my friction is 12 cos 40. Alright, so now if I'm writing Newton's law, this thing is going up and down. I have got 16 sine 50 is going in the positive direction, minus mu times 16 cos 50, minus my 12 cos 40, minus my 12 sine 40. And all that is equal to 0. So this just eliminates t. If I look at the system, what I do is I write the whole thing up and I just take out my t's. Okay, so now I'm missing a mu somewhere. My mu cos 40 should be in here. Okay, So let's add up my mu's. I'm actually going to take my mu to my other side. So on this side, I've got 16 sine 50 minus 12 sine 40. Okay. Okay, and that gives me 4.543. And on this side, so I've got a mu of 233 if I am looking at significant figures, 3 significant figures. Okay, so that I think was the easiest. The other way to do it is exactly what I've done here, split up both the particles and then do simultaneous equations between these two. So then you can solve for t and you can solve for mu. But yeah, this is actually the easiest. I could have done this all in, this many lines. That's actually the amount of space that I used. So don't be intimidated if I give you 2 pages of work. You might not need to use them all. Okay, let's look at question 6. So just to orientate ourselves, we've got 2 questions left here. Okay, so let's go. A car of mass that is moving on a straight road on a horizontal section of road. So just look at the way the question is asked. You've got your introductory paragraph, so the mass of the car is not going to change. Then it says on a horizontal road. So now I already know later on it's going to be inclined. Okay, so just the way that they set up the questions is good to note. Okay, so on a horizontal section of road, the speed of the car is constant, so 30 meters per second. And there's a constant resisting force of 650. Okay, if it's going the constant speed, and there's a resistance of 650, and it's just on a flat road, I know that my driving speed is 650 as well. Calculate the power developed in the car of the engine. Okay, when you see power, you can think of 2 formulas. Power is work done divided by time, or power is force times velocity. In this case, I've already got my driving force, and I have also got my velocity. So that is quite straightforward. So 650 times 30. So 19,500 watts. Please note these questions, they're saying in kilowatts. Okay, so you must just take note of power questions that often ask for kilowatt. Okay, it is given that the power is suddenly increased by 9. So not 2,9, but by 9. Find the instantaneous acceleration. So power plus 9. Okay, so that's going to give me 28.5 kilowatt. Okay, power is driving force times velocity. Okay, what you need to know is that velocity is not going to instantaneously change, even if the power does. So you can use the previous velocity. You must use the previous velocity. And what this does is gives us a sudden new driving force. Okay, so this is the tricks of these questions. Okay, so now I've got my resistance of 650, but I've got a driving force of 950. So I can immediately see that I'm going to accelerate. And 1300. So my acceleration is going to be 3/13. Okay, so I like that, but if I were to round it off, it would be 0.231 meters per second squared. Okay, so the trick with these types of questions is acceleration and power can jump. Your driving force can also jump. but your velocity can't jump. So you need to use this velocity, the velocity at the point, to work out the instant acceleration. Okay, now, next question is on a section of road incline. So now there's an incline, my alpha. So my alpha is equal to that. So if I just were to rewrite this, sometimes I like to do that. Okay, 0.08. Okay, the resistance to the motion of the car. All right, so now we're given the resistance, but the resistance is determined by the velocity. Okay, the car travels downward along this section of road. Okay, so it's actually going down. So maybe my resistance must act up. Okay, probably should have read the question a bit first. Okay, my resistance goes up. The car is going down. It's just some steam there. Okay, the car goes down along the section at a constant speed with the engine working at that much power. Find the constant speed. Okay, constant speed means the forces going forwards is equal to the forces going backwards. So, and because it's going down, our weight is helping the car go down. So we need an mg sine theta, or in this case alpha. It's going down. The driving force is also going down. There is a driving force because there's power in the engine. Okay, so the sum of my forces is mass times acceleration. This car is going down, mg sine theta, plus my driving force, minus my resistance. Put in a bracket here, otherwise you're going to end up not minusing all the terms. Minus my resistance force is equal to my mass times my acceleration. And it's going at a constant speed, so actually this is times is equal to 0. Okay, my mass is 1,3. My sine of, I keep putting theta, but anyway, plus my driving force. Driving force is the same as power divided by velocity. Okay. Velocity, so that's just helpful to write it like that. Minus 1,000, and then here, minus 20V. Okay, so it's good to just make sure you had that in brackets. So let's simplify as I go. 13000 times 0.8. My power is okay. All right, now I'm starting to see something where I'm going to have to get rid of my v in my denominator. So I'm going to multiply all my terms by v. But before I do that, I'm going to put my, I'm just going to summarize this. That's going to be plus 40. Okay, so if I multiply it through by v, I am now getting a quadratic. So now I'm going to divide through by minus 20. Okay, and there I've got my quadratic, so I'm going to do my minus 575. Okay, my velocity is either 25 or my velocity is minus 23. Okay, so it's not going at a negative velocity, so that's not applicable. So my velocity is 25 meters per second. All right, let's see how quickly we can do the last question. Okay, so immediately when I'm seeing loads of equations, I'm thinking kinematics with varying acceleration. Okay, so particle moves in a straight line, so that's kinematics. From a starting point, before it comes to instantaneous rest. So it's going at a, it's moving and then it comes to rest at point X. Okay, the time t after leaving is given by that. So there's three sections here. So here we have a quadratic, and then a straight line, and then a funny curve. Okay, it's just good to know what's happening. So these are my velocities. It is given that there's no instantaneous change in velocity at t is equal to 8. Find the distance OX. Okay, so what is x? X is where it comes to rest. Okay, so I've got to figure out where is the velocity equal to 0. Then somehow I've got to work out the distance. So let's just wrap our heads around this here. They also say there's no instantaneous change where the time is equal to 8. So basically, if you look at these two equations, this one is going up to a time of 8, and then this one is starting at a time of 8. So let's just first figure out what's k. That's 0.9 times 8. So I just want to see at t is equal to 8 what's happening. So my velocity at that point is 30.6 is 23.4. Okay. Right, that's my velocity at that point. And if I look at my second equation, plus kt, I'm actually going to replace my t's with 8's. That must equal 23.4. So I can solve for k. Right, so 23.4 minus, okay, divided by 8. So my k is minus 1 over 5, or minus 0.2. Okay, so at the moment I'm just solving unknowns here, minus 0.2. Okay, so what we want to see is find the distance OX. So when does this particle come to rest? So if I look at my first equation, that is a quadratic, a smiley face quadratic that is very, very stretched by 7.2. Okay, but it's starting at 0, and it's going to go up to 2, so 7.2 times 2 squared. So it's going to have a final velocity here of 28.8 when this thing is 2. Okay, then we've got a straight line with a negative velocity. Okay, so I just want to work out at 8. What's happening at 8? We already worked that out. It's 23.4. Okay, so it's probably going to not then cross the x-axis. Let's just take a look at what's happening at 2 seconds. So 30.6 minus 0.9 times 2. 28.8. Okay, so it doesn't yet cross the x-axis, so it looks like it only crosses, I should rather say the t-axis. Okay, so then it's going to also start there. So something's happening in the last bit. So we need to find out where does it cross the axis. So I'm going to say minus 0.2 t, and I'm going to make that equal to 0. So that's where it's going to cross the x-axis. Let's multiply through by t. So 1600. Okay. Okay, so at 20 seconds. So how did I find that? They want to know when does it come to rest. So I made my velocity equal to 0. So at 20 seconds, that thing is going to pass across the x-axis. Okay. Now we need to work out what distance this particle is away. So remember, if you keep an eye on your drawing here, so this is going to cross somewhere at 20. We're basically looking for the distance under all these curves. And this is a 9-mark question. Oh, and it's the only part of this question. Okay, so we can just, what I can see is a lot of work, but it seems to make sense. Okay, so because my first equation is a curve, I'm going to integrate between 0 and 2. Okay, and that was 7.2 t squared. Okay, the reason I'm integrating is when I go down my line, I differentiate, and when I go up, I integrate. Another reason is because on my velocity time graph, my area under the curve gives me the distance or the displacement. Okay, so I'm going to integrate here between 0 and 2 to find my first area. Okay, and then it's a definite integral. I'm going from a specific point, 2 to the power of 3, and then that's just going to be minus 0. So 7.2 divided by 3 times 2 to the power of 3, that gives me 96 over 5, or 19.2 meters. Okay, so in the first 2 seconds, this particle traveled 19.2 meters. Now, I'm just going to look at my trapezium here. I'm not going to integrate. I don't need to integrate. Although it is going between 2 and 8. So my area, you can integrate it between 2 and 8, but I'm going to say, because I know my two values here. My length is 28.8, and my other one is 23.4. So those two lengths divided by 2, and then it's going for 6 seconds. So I personally think just working out the area of the trapezium is going to be easier. Although you can definitely integrate the line between 2 and 8. And here we get 783 over 5, or 156.6 meters. Okay, and then our last bit, I know now that it comes to rest at 20, so I'm going to be integrating between 8 and 20. I've got to integrate this line, so I'm just going to set it up here. I'm going between 8 and 20. See, so that's my final area that I'm looking for. And then we've got to add up these 3 areas, and hopefully that is going to give us the right answer. So just before I integrate here, I need to bring my t up, the -2. Okay. So that's minus 1600 over 20. And then I'm subtracting. And if we look at this, minus 1600 over 20. And we get an answer 432 over 5, or 86.4 meters. So I am now going to be adding up all these distances. So 19.2 plus 156.6 plus 86.4. And that gives me 262.2 meters. That is my total distance. A question like this, I really find it helpful to know, first of all, what kind of graphs are you looking with? Straight lines or curves? Okay, because then you know when you're looking at the area whether you have to integrate or whether you can use geometry. So that's my first tip. Second tip is to have an idea of what the sketch looks like. It really, really helps you to understand what's going on. Yeah, and then third, just knowing the relationship between displacement, velocity, and acceleration. And going down is differentiating, going up is integrating. Or in this case, just looking at the area under the curve, you know, that's integration if you think of pure math one. So that's how I like to face these questions. I hope that that was helpful for you. That is this paper complete.